Cambridge University Press 2015, and Compress Sensing for Engineers, published by CRC Press 2019. He has co-edited two books, Deep Learning in Biometrics and MRI Physics, Reconstruction and Analysis, both published by CRC Press. He has two granted US patents and six more filed. Anshul has been the chair of the IEEE SPS Chapters Committee Membership Board from 2016 18 and served as the chair of the SPS Educational Committee 2019. Currently, he is a member at large in the SPS Educational Board. He has a strong connection with the industry. He has been the research advisor to Tata Consultancy Service since 2017. So, sir will be delivering lecture on collaborative filtering, aka recommender systems. Sir, I will request you, you can start.
Thank you for the kind introduction. So please interrupt me whenever you have some questions. So let's start with collaborative filtering. So I think like all of us kind of know what it is, but still, for the sake of completion, we will just briefly review it. So like basically collaborative filtering is the algorithm, the de facto algorithm that goes on behind all kinds of recommenders that we see today. Like if you're visiting Amazon, we see that items like similar, you'll see a list of similar items. Or like people who have bought this have also bought this. So same when we go to Netflix we see that like I think the past month they have started this service where based on our like preferences, they will automatically download some shows or movies for us. The same thing goes in Amazon Prime. So based on our choices, it starts like telling us customized recommendations of what we might like. So anything like that requires some kind of a recommendation is at the back end using one form of the other of collaborative filtering. Now now why is it required? Why is it useful for both businesses and the customer? Now for businesses, especially in this kind of like an online B2C scenario, they can only improve their bottom line if their revenue increases, and they can increase their revenue if people buy more or the people rent more. So something like that, like whenever they can sell their services or their products, they can make a revenue out of it. So it's extremely important for the businesses. So that's why like Amazon and basically all the companies have their own teams for improving their recommendation systems. For customers, we also need recommendation systems because there are like whenever we visit any of these sites, there are like at least hundreds and thousands, if not millions of items to choose from. So what I will like, that frankly speaking, I don't know. Right. So like so that is the reason we need recommendations. Now let's take a step back and see how recommendations have been done in the past. So like this is a screenshot of my screen when I haven't logged into Amazon. So see that like it's telling me like I think it's from like a quite a while back this was taken. So it's just giving me like asking me like Kindle Unlimited, what are the different types of product that everybody is used. So this is what they're telling me. So now the difference between a recommendation and this kind of traditional means of reaching out to the customers is that recommendations are personalized. Advertisements are not. Advertisements are just popular. Like here, Amazon is telling me what they want to push. Either that they're advertising that, or they're telling me which ones have been used or bought the most. It's not customized at all. The same thing, if we are looking at recommendations in the past, we are looking at say like a movie recommendation. So we find that in the papers or the recommending dresses and all that from the past, like for more than 100 years or more than 100 years, we have relied provided reviews for recommendations, expert reviews rather, or we have asked our friends, did you like this movie? Did you like, what is this movie about? Did you like this book? So basically, while growing up, we figured out like my taste matches with my friend's taste. So if he or she likes it, probably I will like it as well. So this has been the traditional way of recommendations. Now, when recommendation system started, let's keep over this example. So I have already told about this. So basically, like I'm looking at a yoga book, and it's telling me what are the items associated with this based on past history of browsing and buying. Okay. So let's start from here. So traditionally, how recommendations were happening was that it was based on either on expert reviews or on recommendations from our friends whom we trusted. So that is how recommendation system started initially. So they were based on the neighborhood based method. So as the name suggests, what it tries to find out is that it tries to find out friends, like virtual friends, from the entire data set. Like they have the data of say I have bought a bunch of items in Amazon. Somebody else has bought some other bunch of items in Amazon. So they are trying to, so from this kind of data, they are going to try to find out like which person does have similar taste as to mine. So if they can find that out, what they're going to do is that for a new product or for a product that the others have used but I haven't, they are going to start recommending me those products which I might like. So that I might like is by finding virtual friends from the entire data set. So let's start with I will go through this, I have kept it very simple so that everybody can understand it, including undergraduates. So let's start with a concrete example. So we have a bunch of users here, U1 to U8, and I took some IMDb top 10 movies. And I've given some recommendation, like some random numbers have recommendations for each of the users. So when a number is high, it means that a person likes the movie. If the number is low, it means that the person kind of doesn't like the movie that much. And there are some blanks. So the blank means that this say U5 has not watched Shawshank Redemption or haven't watched 12 Angry Men or Dark Knight. That is what it means. Now, what our toy problem that we want to solve is that should the good, the bad, and the ugly be recommended to the user U2? In other words, what we are trying to predict is that what will be the expected rating of U2 on the good, bad, and the ugly. If the rating is high, the system is going to recommend it. If the rating is low, the system will skip it. It's not going to recommend it. Okay. Now we have to find out who are the similar users. Now we can only find out the similar users if after we have removed this item. So that is why there is a big cross on good, bad, and the ugly. For the rest of the data, we are going to use the ratings of the users on the different movies to find out who are similar in nature. So of course I can't use this is natural that we are going to remove that movie or the item for which we want to find it out, right? Because this question mark means that we don't know it. So basically we won't be able to compute any kind of similarity with unknown values. Okay. So hope this part is clear. Now what I do is that I find out the cosine similarity between different users like U1 and U2, U1 and U3, so on and so forth. So of course it's going to be a symmetric matrix. So we have just looked at the the top triangle, the triangle above the diagonal. That is the one we are looking at. So we have computed the similarities between different students. So here I have using cosine because it's easy. But anybody, if somebody wants, they can use something else like Euclidean, Manhattan, or Pearson or some other kind of correlation. So just we should bear in mind something. So that is for example, when I'm computing the similarity between U1 and U2, see that U1 has not watched Pulp Fiction, but U2 has. Similarly, U1 watched Schindler's List, but U2 hasn't. So whenever we are computing the similarity between two users, we should only compute the similarity between the items that both of them has rated. For example, for Pulp Fiction, when there is no U1 rating, we can't compute the similarity because it's an unknown value. So unknown value we should not be imputing by zeros. It doesn't mean it's zero. It just means that it's unknown. So we should not be considering Pulp Fiction and Schindler's List when we are computing the similarity between U1 and U2. So that is the reason I have used cosine. So in cosine, it doesn't really matter. Cosine, you can just take this as 0 and then compute for the entire vector. So it will be exactly the same value. But you are using some kind of like a Euclidean distance, or like the inverse Euclidean distance rather. In that case, you have to be careful to not take items that are not correlated. So that is what we call like correlated, or like that is the technical term. We should only consider similarities between correlated items. So moving on. So this is what we found out. Only on correlated items is the similarity that we get. Now we want to find out users who are similar to U2. That is our goal, right? So let's see. So we will see who are the nearest neighbors. So the nearest neighbors for U2 are U4 0.89, U6 0.86, and U1 0.63. So that is what we have here. Now the rating is okay, not exactly. So we have here U1, U3, and U6. U1, U3, and U6. So U4, but the similarity for U4 is high, right? But we haven't considered it. Let's see why. That is because U4 has not even watched Good, Bad, and the Ugly. So there is no point in considering U4 because there is no rating. So we can't be using U4's rating on Good, Bad, and Ugly to find out what U2 is going to do, right? So this is the reason something which has not rated that particular item cannot be considered. That is like just common sense. So that's why instead of taking U4, we have taken the next best 3. So that would be like U1, U3, and U6. So you have U1, U3, and U6. Now the question is, how do we estimate it? Now the simplest way what people have used is that they have used the normalized similarity scores as weights for interpolation. So we have like 0.86 into 5 plus 0.63 into 4.5 plus 0.56 into 3, and then the normalization term and the denominator. So we end up with getting something like 4.3. So basically it means that like the Good, Bad, and the Ugly should be kind of recommended to U2. So this is like a pictorial description here. So we have 0.63 for this. We are multiplying 4.5 by 63. We are multiplying 5 by 0.86, and then we have this U3. We are multiplying 0.56 by 3, adding everything up, dividing it by the weights, and we have our answer. Okay. Now, let's go back one slide. So look at this something. So there is no reason that we should be actually using this normalized similarity score as the weight metric. So that is not what we do interpolation, right? So this is just some arbitrary value, arbitrary way of doing it, and people have been using it forever. So somebody has said that instead of using like the similarity value, if you take the square of the similarity value and then normalize it, you get better results. So basically, it is like a lot of heuristic is going on. Okay. So it's understanding is fine. Like there we are trying to find out friendly virtual friends, looking at their ratings and then interpolating them. But the understanding and interpretation is fine, but then it's not very like mathematically well grounded. So that is the reason there is a lot of like hand waving that goes on out here. And to the best of my knowledge, nobody who is doing research in this area are using this kind of like neighborhood-based similarity for recommendations. Okay, so like if we summarize what we have learned so far, so that would be basically we are using linear interpolation. That's all. So the Rij with the cap is the rating that I want to estimate. So the rating of the user I on the jth item. What we have is that Wik, which is basically the normalized similarity between the user I and the kth user, and Rkj, which is the rating of the kth user on the item j. And this k belongs to Ri, means that Ri is the neighborhood that we are considering. So in this case, we have considered 3 neighbors, so like that. So it's a simple linear interpolation problem. The only issue is that this Wik, this is not uniquely determined, so that is left to interpretation or some heuristic hodgepodge that goes on. So the another approach which is never very popular is recommendation as a classification problem. So let's take another example. We have 4 users, Denny, Alan, Shirley, and Paul. And we have 5 shows: Sherlock, Game of Thrones, The Big Bang Theory, Modern Family, and Breaking Bad. Now say we know Denny's what to say, likes and dislikes on all the 5 shows. Same for Alan and Shirley. But we don't know what if Paul is going to like Breaking Bad or not. So this is the value we would like to know, if Paul is going to like or dislike it. So here we don't have, well, of course, this we can think of like and dislike as rating, something like -1, 1, or 0 or 1, whatever way we like. But we can keep it categorical as well, because we are formulating it as a classification problem. This is just what I say. Like we want to find out if Paul is going to like Breaking Bad or not. So you are posing it as a supervised classification problem, and let's take this that like each item will be considered as one sample. So here item means that the shows users are like Paul, like Denny, Alan, Charlie, and Paul, and the items are like the 5 different shows. So just for the sake of it, instead of writing, because you have to write dislike, like, and dislike, so I have written like as +1 and dislike as -1. So Paul's choice on each item becomes the class label, and the Denny, Alan, and Charlie's rating on each item become the features. So please stop me if I am like this can be slightly confusing, because everything is basically a like a bunch of likes and dislikes. So how are we categorizing features from the class label? So what we did, if we're looking at this slide, is that we are taking the last row as the class label. Like Paul's choices, we are taking as a class label, like dislike, what I have encoded as -1, -1, and like as like +1, +1. So these are my class label, and the rest of it, like for Sherlock, Sherlock will be represented by a vector of size 3, like 1, -1, 1. Similarly, Game of Thrones will be represented by a vector of like size 3, -1, 1, 1, so on and so forth. So let's get back where we were. We were here. So that's how we have created these labels and the corresponding features for each matrix. Now let's take 2 examples. Like let's start with the simple nearest neighbor approach. So as I was saying, like we are not using anything like very recent state-of-the-art methods. It's a very like the basic introduction to collaborative filtering talk. So like the expanded version of it I gave for the first time in 2014 at the UBC summer school, and after that, like the abridged version, the one that I'm presenting today, I have or rather some version of it I have presented at like different places in India, like Indian Institute of Science and IIT, not IIT, ISI. So the version that we are studying today is that one, meant for a very basic level of audience. So that's why we will just cover like 2 types of classifiers: nearest neighbor and naive Bayes. So nearest neighbor. So since this is kind of a like the features are binary values, so what we thought is that using the Hamming distance will be the most obvious choice. Like if Hamming distance between 2 strings is basically where like the number of points where the strings are vary, like Caroline and Catherine, K and IN at the end are the same, but in the between Caroline has ROL and Catherine has CHR, so the Hamming distance is 3. The same we can also find out Hamming distance between any bunch of symbols, right? Okay, so what we want to do is we have to find out, like the way we proceed in nearest neighbor is that we take the test sample. In this case, the test sample is Breaking Bad, and we want to find out the distance between the test sample and the remaining training samples. So in this case, the training samples are the ratings on Sherlock, Game of Thrones, Big Bang Theory, and Modern Family. So we have found out the Hamming distance between Breaking Bad and the rest of them. So it turns out to be 1, 1, 3, 10, 3. Right. Now Sherlock and Game of Thrones are at least in this data set, are the nearest to Breaking Bad. So what are we going to do? We are going to say that we are to say whatever is the class level of Sherlock and Game of Thrones, we are just going to impute the same value. We are going to assign, not impute. We are going to assign the same value to Breaking Bad. This is exactly what we do in nearest neighbor classification, right? We take the sample, like the test sample, we find out the distance of the test sample to all the training samples, and then we find out who are the nearest training samples, and looking at their corresponding class levels, we assign the class level. So there are some nitty-gritties here and there. So for example, what would have happened, say, if Sherlock and Game of Thrones, if Sherlock gave -1 and Game of Thrones was +1, false ratings, I mean. So in that case, there would be a tie. So this is just a toy example, but usually when we have like a lots of data, there is hardly any problem of ties. But even then, if there is a problem of ties, we use the concept of K nearest neighbor, where we keep K to the odd, so that we can use majority voting to peel off any kind of tie. Okay. So based on whatever analysis we have done so far, we are going to assume that Paul will dislike Breaking Bad because it turns out to be -1. The same thing we can do using a naive Bayes assumption. So in naive Bayes, the general formulation, what it has here, we have C classes with labels say W1 to WC, and we have a bunch of features like X1 to XD, that's the T length vector of length T. Now in the naive, like the reason it's called naive Bayes is that what we assume is that the P of X given Wj, like P of the feature given the class level, is independent, meaning independent in the sense that like it will be actually P of X1 to XD given Wj. We are making the assumption that X1, X2, X3, so on and so forth to XD are independent from each other. So that is why the naive part comes in. So naive Bayes assumption, for like I will give you an example where it doesn't work. It doesn't really work in image processing. Like if I have X1 to XD as features of the as pixel values, and we assume that like all the pixel values are independent from each other, that's a totally wrong assumption. Like images have a lot of like local redundancy, local correlation. That is the reason CNNs work. So if there's such kind of naive assumptions should not be made for any kind of data. But again, this is the simplest one, and that is why it's naive. So you can write P of X given W, like capital X given Wj is actually product of all of P of small xi given Wj. So what we want to do is that we want to in naive Bayes we want to maximize the prior. So if you take the full Bayes theorem, we want to find out P of Wj given X, like what is the probability that Wj is the class level for the feature X, capital X, that we want to find out ideally. So we have like by Bayes theorem, we have this P of X given Wj times P of Wj by P of X. Now, like P of X is kind of constant, so we don't really care. We just want to, like in the simplest case, we just want to look at the numerator part of it. So that is what is done in naive Bayes. Like we assign X to the class where P of Wj given X is maximized. So now comes the independence assumption. So we like as we discussed before, P of capital X given Wj, we can write it as a in the product form, assuming independence. That is that part where product over I P of xi small xi given Wj, and we have that P of Wj that is from the prior on the W. So let's see how we actually can use this for the problem that we have. Now for estimating the prior, we just look at how many times a particular class is occurring in the class labels. So here what we see is that like minus, there are two class labels, -1 and +1. So -1 is appearing twice and +1 is appearing twice. So basically what we're going to have is here is that P of W1, Wj equal to -1 is going to be 2/4 or half, and P of Wj equal to +1 is also going to be half. They represent equal number of times. Now comes the part of computing P of small xi given Wj. So each of the xi's can take a finite number of values, like number of discrete values ak. So now this is represented by n of jik by n of nj. Now this might look slightly confusing, but as we go through the example, that is going to become clearer. Okay, so this is the problem that we want to solve. So as I said, P of W equal to +1 is 2/4 and P of W equal to -1 is also 2/4. This we get from just by looking at the labels. So this is the prior on the labels. Now comes the part of the features where we are computing the P of small xi given Wj. Now let's come here. So we are looking at this guy here. So we have P of W equal to 1 given xi equal to -1, x2 equal to -1 and x3 equal to +1. Okay. So x1 equal to -1, x2 equal to -1, x3 equal to +1 basically is the feature for Breaking Bad. Now we know what is P of W equal to 1. This is 2/4, and then for the rest of it, P of xi taking the value -1 when W equal to +1. Let's see when that is the case. Xi is -1 when W equal to +1. That is for the case where where W equal to +1. So there are no cases. So we are looking at x1 equal to -1 for W equal to +1. So that is there is no case. So that is why we get 0/2. I mean everything is going to be 0, but still if you want to plow through this, all of them are going to be 0. So you can just completely write that P of W1 given W equal to +1 given capital X is going to be 0. Now let's look at what is going to happen for the other probability P of W equal to -1 given this feature vector -1, -1 and +1. So P of W equal to -1 we already computed, that is 2/4. Now P of x1 equal to -1 when W1 equal to -1 is x1 equal to -1 when W1 equal to -1 is half, right? So here it's -1 and in this case it's +1. So it will be half. See, we have half here. Similarly, P of x2 equal to -1 when W equal to -1 is x2 equal to -1 when W equal to -1, that is here, is again half. One is 1, the other one is +1, so half. Similarly, for the case when the x3 equal to +1, when W equal to -1 will be 2/2, that is 1. In both cases, we are seeing that is +1. So that is what we have here, 2/2. So we have like this unnormalized probability of P of 1/8. So here is basically there is no 0 probability, and the other one like dislike has a probability like a finite probability. We are going to say that Paul is going to dislike Breaking Bad, right? So this is the same answer we got using nearest neighbor approach with Hamming distance. Now, as I said before, that in the past that neighborhood-based models have been used, and in the classification-based approach, although there hardly anybody used it. It's really complicated, and the bigger problem than being complicated is that what I gave an example here is a toy example. Of course, for all the users, we are not going to find out all the values to be rated. So in that case, like there will be a lot of features with missing values. Now, lot of features with missing values is always troubling in machine learning, right? So that is one of the major reasons that it has not been used in kind of a classification kind of a model. But things are changing these days. Everybody is trying to use deep neural nets like deep CNNs for collaborative filtering. So in the past couple of 2-3 years, a lot of work has been done in this area as well. Now, what is actually of you, and the latest, at least the research goes for collaborative filtering is based on something called the latent factor model. Now let's take a step back and let's try to understand how do we choose an item. For example, how do we choose a movie? So we look at who are the actors. We have our favorite actors. Who is the director? We have our favorite directors. What kind of a genre does this movie belong to? Or maybe at most we are going to look at who is the producer or who is the cinematographer. We look at a bunch of factors before we choose that we are going to watch this movie, right? Now, if you are looking at, if you are thinking about a book, there are even fewer factors. Most of the times, we just look at who is the author of the book. If Session-2 is the author of the book, probably I will read it. If Bimal Kaur is the author of the book, probably I won't read it. Something like that. In the most number of features or aspects that we might looking at while choosing the book is what is the genre of the book or what the book is about, right? So what we're trying to show is that there are only very few factors that actually determine our choice on a particular item. Now, this was the basis of something called content-based filtering. So content-based filtering is a pretty standard approach in information retrieval. This was tried to be used for collaborative filtering, never really panned out. Now, what content-based filtering does is that it creates a profile of the user and the item. Like, for example, we are taking the example of movie. So we are looking at, say, what kind of a movie it is, what is the star cast, who are the producers, who are the sponsors, who are the cinematographers, who is the music director. We might see we might have to consider a lot of items, right? So that is for the items part. Now computing of a profile for the user is even difficult. What they're going to do is that they want to find out a profile like, does Angshul like A.R. Rahman? Does Angshul like Sonu Nigam? So they're going to create such a bunch of factors for each user as well. Now they're going to match. The matching part is very simple, usually cosine matching, and then based on the cosine similarity, they are going to tell me what movies to watch. Now, why this is fallacious is I will explain in a second. Now, how many considers should we consider? How many features should we consider? That nobody has really an answer to. So it was dependent on a lot of heuristics, like it requires experts to model movies, to model books, and all that. And even then, you are never sure if you have missed something or not. Say, for example, I'm giving you an example. Say, in most cases, I don't really care who is the music director unless it's A.R. Rahman, right? So if somebody is trying to model me without without considering the music director, then it won't give very good results, right? Or say example, I don't really care who is the cinematographer unless he's my friend, and Professor SPM knows him very well, like my batchmate from IIST, Devashish. So he, after studying his BTech, he went to Pune, studied cinematography, and now he makes now he's a cinematographer, established cinematographer. So probably I don't really care about who is the cinematographer unless it's Devashish's movie. Even if the movie doesn't have very good reviews, I am definitely going to watch it. So this is what I'm trying to say. So explicitly, it's almost impossible to catch the number of factors that are responsible for a person's choice on an item. So this is where latent factor model comes in, right? So what latent factor model says is that we are going to assume that there are a bunch of factors which decides our choice on an item, but we don't need to exclusively know what are those factors. We are going to learn it from the data. Now, let's take another example. Say, say, just for the sake of it, let's And let's think that our choices on movies are only decided by the genre of the movie. If it's action, I'm going to watch it. If it is a comedy, I might be watching it. If it's a drama or a romance, I want to watch it. Things like that. Now, each of the, like, how do we model the items? The items possesses this feature to a greater or lesser extent, or a user might have a propensity or affinity towards each feature to a lesser or a greater extent. Now, when this is going to be a good match, means that this propensity and the amount the item possesses that feature is going to match, only then the rating is going to be high. Okay, so for example, let's say like I want like a little bit of action, a little bit of comedy, zero drama, a lot of thrill. So when the movie matches those conditions, and then then I am probably going to like the movie. Then the rating of, and then I'm probably going to rate the movie as high. So the simplest way to do it is just a cosine product, right? Cosine product. Now there are a few other things that we must consider. For example, there is something called user's bias. So sometimes the users are very critical. Say, for example, like I might be very enthusiastic about everything, and even if I don't like the movie, probably I will rate it 3. I will say on a 5-point scale, I rate it 3. And if I like the movie very much, I will rate it 5. Another person might be very moderate. So they will rate every movie between say 2 and 4. Or somebody might be highly critical or rate everything between 1 and 3 or 1 and 4. So the rating exactly, like individual ratings don't tell a much unless you're looking at the context of the user, how he or she has rated all other movies. So what the way that it's explained is there is a user bias to it. Similarly, items also have bias. So if a movie like a Titanic or a Ben-Hur or Lord of the Rings come like bagging like 10 plus Oscars, people have those movies already have a positive bias. So they like people will definitely rush towards the hall to like watch those kind of movies. Or people like say, I'm just giving an example, Ram Gopal Varma Ki Aag. Nobody liked the movie. So that kind of a movie will have a negative bias. So we don't want to really want the item bias or the user bias. We want to get rid of it. So that usually the way the bias is termed is deviation from the mean. So mu is the global mean. Rij is our rating of the ith item, or the ith user rating on the jth item, doesn't really matter. Bi is the items user bias, and bj is the items bias, right? So this is usually modeled as a summation, and there are ways to estimate it. The easiest way to estimate is using Potter estimation, but a more data-driven approach to estimate is that I want to learn Bi and Bj. Mu is a global mean, so nothing to learn, by minimizing the fit. Of course, I don't want to completely minimize the fit like Rij minus mu plus Bi plus Bj. That will be overfitting. So we have some regularization parameters like Tikhonov regularization parameters on the variables Bi and Bj. Okay. So formally, if we put everything together, what we have is that Rij is a summation of the bias of the baseline model and the interaction model. The interaction model means Ui transpose Vj, like the interaction of the items and the users' latent factors. Now this is how we put everything together, like Rij minus mu minus Bi minus Bj minus mu I transpose Vj. This is the entire cost function I want to minimize. And of course, I regularize it by some Tikhonov kind of a regularization. So this we can solve by minimizing each of the subproblems Bi, Bj, U, and V. So traditionally, people just use some kind of what to say like gradient descent or like a gradient descent kind of an approach to solve it. Or you can, like, if you are thinking of neural networks, some kind of a backpropagation approach to solve it. Okay. So if you're looking at a holistic view, what we have been trying to do so far is we have users along the say rows and items along the columns. This entire matrix is highly undersampled. Like we have very few ratings available, and most of them aren't available to us. So what we are trying to do is we are trying to complete this matrix. If we have the complete matrix, we will know what is each user's expected rating on that item, and we are only going to recommend those items which have predicted higher ratings for every user. So this is basically a matrix completion kind of a problem. Okay. So and why is it low rank? It's a low rank matrix completion problem because, as we just mentioned, the choices or the factors that decides if we are going to like a item or not is finite. Like if there are say like a typical like a blockbuster will have say like thousands of people involved, but not more than 20 or 30 factors will be there. Okay. Or there can be like, if in this matrix there can be like hundreds and thousands of users and hundreds and thousands of items or movies. But the number of factors that decides our choice on an item is going to be very small. So that is why this matrix is going to be a low rank matrix. So the way we solve it is that we model the matrix Z, a low rank matrix. We have M, which is the mask on that matrix, and Y is the observed rating. So basically M is a binary mask. We have 1 where the rating is observed and 0 elsewhere, and then some kind of a Gaussian noise eta. So I know M, I know Y, I know the statistics of eta. My problem is to solve Z. Now using the latent factor model, we have modeled Z as a multiplication of the user's latent factor U and the item's latent factor V. So instead of Z, I can write it as a product of U and V. So this is our complete model. The task now boils down to a typical like a matrix factorization problem where we have to estimate U and V. This we can do by iterating in every iteration. Like alternating in every iteration. So for every iteration K till some kind of a convergence criteria is met, we will estimate we will estimate V assuming that UK is constant, U is constant. So U is constant meaning we are taking the previous value of U. And then we are going to update U assuming V is constant. Okay. This is the most standard approach for matrix factorization. There are different ways to do it. For example, like one popular approach is non-negative matrix factorization, which kind of says that our the latent factors cannot be negative. It should be either 0 or positive. So what happens is that the same update for V and U remain the same. But after every update, we need to make sure that we are only taking the positive values that we have solved for. Okay. We can regularize it by some kind of an L2 regularization on U and V. So I'm going to finish my talk in another few minutes. After that, there will be enough time for question and answers. Or it can be something like let's be on this slide, and I will tell you the idea for moving forward. So if you are solving it like a regularized matrix factorization with L2 regularizations on the U and the V, L2 regularizations will ensure that there are U and V, that the item latent factors and the user latent factors are dense. Okay. Now let's see if this is a good assumption. Say for example, let's go back to the previous example that we took. Say the latent factors for the movies are only the genres and ignore everything else for the time being. It's a toy example. So I might have some finite propensity towards each genre. I might like thriller or action more, romance and drama less, comedy a lot, something like that. But it's not possible for an item to possess all kinds of latent factors, right? If you take another example, say like an example of a shirt. Say I want to buy a t-shirt from Amazon. I might like green less, I might like yellow more, I might like pink less, I might like blue more, something like that. Right. So I might have a propensity towards each color. If we just assume that color is the deciding factor of the shirt, I might have propensity towards each color to a higher or lesser extent. But a shard, right? A green shard cannot possess any propensity towards being blue, right? So what I'm trying to say is that an item cannot have a propensity towards all kinds of features. So by the nature of itself, item matrix cannot be dense. So the solution to have the item matrix U to be regularized by U2, like an L2 norm, is kind of fallacious. Sorry, item matrix is V. U is the user's matrix. So instead of having an L2 norm on V, one of my students figured out that if we have a L1 norm on V, it will be a more sensible formulation and is going to lead to better results, right? So this is what we did, and we found out that that is actually the case. Like if we have like a standard model for like SGD, SGD is the like the solution, a solver, but it's solving a matrix factorization problem. And then we have like the matrix factorization with L2 norm and L1 norm, or a combination of combination of both, and we find that actually a combination of both works the best in terms of error in AER or RMSE. Okay, so matrix factorization is just one approach to solve it, but broadly speaking, what we want to solve actually is a matrix completion problem where the matrix is low rank. So matrix factorization is just like a standard approach to do it. It's easy to solve. It has been used a lot in the past, but the problem is non-convex. It's a bilinear problem, right? We don't like both U and V are unknown to us. So a much better approach to solve it is actually to find out a matrix. So of course the problem like y equal to MR is underdetermined, right? So R is a dense matrix with a lot of values, but we can't see all the values. We have Y, which is basically a subset of R. So if you want to find out the bigger matrix, when the solution space is larger than the observation space, the problem becomes underdetermined. Now, since it's underdetermined, it's going to have infinitely many solutions. So what we mean here is that we want to look for a solution based on the nature of the problem. We want to look for a solution which has the minimum rank. Okay, so that is for the first equation we have here. We want to find a minimum rank solution with the constitutes of data fidelity term. But find rank minimization is like exponentially hard, like NP hard. So what it does is, what people have done is that they have relaxed the rank minimization problem to its nearest convex surrogate, which is the nuclear norm. So nuclear norm is nothing but the summation of the singular values. Using nuclear norm minimization, mathematicians have proved that it's also going to guarantee a minimum rank solution. So which is good because there are a lot of solvers for nuclear norm minimization, right? So what we like this is just so like the main topic that I wanted to discuss is over. This is just some heuristics that we use that we solve the nuclear norm minimization. Like nuclear norm minimization problem, the problem with that is that it requires computing the singular value decomposition of the matrix at every iteration, which is what to say, like a pretty time-consuming process. So if we if we take a very standard data set, which is the 100K movie data set, and do a 5-fold cross validation, like a standard matrix completion, matrix factorization is going to take a lot of time, like 150 seconds. Matrix completion, which requires, as I said, like singular value decomposition, is going to be even slower. But if we go for our just some like a change in optimization, we can solve it actually very fast. This is for the 100K data set, like the Netflix data sets and all that will be in millions. So you can imagine the time we can save using such a technique. For bigger matrices, when we can't solve everything together, we want to do divide and conquer. So divide and conquer. So it is like a very good paper on matrix completion by divide and conquer by Session-2. So what McKay proves is that if you have a big matrix and you divide it into a bunch of sub-matrices either along the length or along the breadth, and you solve and you complete each of these sub-matrices, column or row sub-matrices, using your favorite matrix completion algorithm, and then project each of the sub-matrices on one of the column, like the column space of one of the matrices, and combine them together. Combine means just positioning them together. You get an optimal solution. So we found out that for the like a smaller data sets, it actually works like this divide and conquer. And see, like if we divide the matrix into just 4 parts, the time requirement changes from 2.67 seconds to point just like less than a second. So for the 110 million data, like a 10M data set, which is a much larger data set, you can see there is a significant reduction in time as well. So the rest of the talk is more into like matrix, like some graph regularized matrix completion. I don't really want to get in there because it will require a lot of discussion, and we are reaching the end of my talk. So I would like to stop here. So basically, the rest of the slides is something like what I'm trying to say is that, which is kind of obvious actually. What we are saying is that if there is metadata associated with your, of course there is metadata associated with the problem. Like for example, the users, for users, the data set will have information about what to say, information about like the user's age, gender, then occupation and all that. So that can be considered as metadata. Similarly, for the item, it will have some textual description from which you can create a table like again, what kind of shard, what is the material of the shard, what is the size of the shard, and so on and so forth. So if those, instead of just you blindly using matrix completion, if we can take into account the metadata somehow, then the solution improves. That is the basic point. So how you can use it, like there are different approaches. Like currently the most standard approach is to use the metadata to compute similarities between users and items. Use the similarity as a graph Laplacian regularization and regularize the matrix completion problem, and you get excellent results. So that's all. So I haven't skipped much. So thank you very much. I'm open to questions.
So we can take questions. If anybody has any question, you can type in the chat box.
So am I supposed to look at the chat window, or am I like, should I expect like questions?
So you can take questions from, if anybody has any questions, you can take it from audio also, but if they're writing it in chat, then you can just take it from chat also.
Okay, let me open the chat. Okay. So I don't think there is any question related to this presentation in the chat.
Yes, I also don't find. Anybody, if you're having any questions, you can put it in chat box.
Hello, sir.
Hello.
Hello, sir. Can you please go to slide number 4 or 5, where you have shown the matrix, upper triangular matrix?
Yes, definitely. This matrix.
Yes, yes. How it is calculated, sir?
Cosine similarity between the users. After omitting that particular item that we are trying to find the rating for. Like if you go back here, so because I want to find rating on. Yeah, so we want to find out.
How?
Can I finish?
Yes, sir.
Thank you. So U2, we want to find out U2's rating on good, bad, and the ugly. So we are removing this item. Then we are finding out the cosine similarity between U1 and U2, U2 and U1, U2 and U3, U2 and U4, so on and so forth. So that is being showed here in this highlighted row. The similarity between U1 and U2 is 0.63, U2 and U3 is 0.56, so on and so forth. So I have used cosine similarity, but you like it can be anything. It can be any kind of correlation, inverse distance. It can be anything.
Okay, 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 sir. Thank you. Thank you.
Okay.
We can take more questions. If anybody has any question, you can just put on your audio or you can put it into chat box. So we can't get more questions. That means they are not typing it in the chat box. We are not getting any questions. So
Okay. So thank you. So let me stop.
thank you. Okay, sir. Thank you, sir, for your wonderful information which you gave and all the works which has been done, which you have shared with us. Thank you, sir.
Thank you.